So, good afternoon, everyone. So, today we'll be discussing week 2 lectures, contents regarding week 2, regarding the course Wheeled Mobile Robots hosted in NPTEL. I'm Isaac John. I'm a PhD scholar at IIT Palakkad, and I'll be assisting Dr. Shantakumar Mohan in conducting the live tutorial sessions regarding the course Wheeled Mobile Robots. So in this week, we deal mostly about kinematics. We have discussed topics regarding generalized wheel model, what are holonomic robots and non-holonomic robots, and what are the conditions of robotic constraints being holonomic or not. And we have also so far considered we have also so far considered some of the kinematic simulations of well-known robotic configurations. So I hope we can go forward with the tutorial sessions regarding week 2. So we'll get on with the questions. I hope I'm audible. Atul, could you please confirm whether my audio visual is all right? Okay, so we'll get on with the questions. So first question is a direct question from kinematics of differential wheel mobile robot. So it says in a two fixed wheel differential drive mobile robot, the left side wheel angular velocity is 0.5 seconds. So we'll get on with it. Left side wheel angular velocity is 0.5 radians per second. And the right side angular velocity is 1.5 radians per second. So omega right is 1.5 radian per second. Both wheels are the same size and the wheel radius is 10 centimeters. So let A be the wheel radius. It says 10 centimeters or 10 by 100 meters. So what is the longitudinal wheel velocity of the robot with respect to its body frame? So this is a typical question that you could expect in your assignment questions. It is regarding a differential wheel robot. So as you might have been aware of differential robots, it has two independently driven wheels. And if this is the body fixed frame, X and Y, we have been given with the wheel velocities. So if I consider this to be the left side, as per the convention, this would be the left side, and this would be the right side. So we have been given with the angular velocities of each of these wheels. If that is the case, then what are the linear velocities at the wheels? So linear velocity V left would be A times omega left. This would be 10 by 100 times 0.5. This would be 0.05 meters per second. And what about V right? This would be A times omega right. This would be 10 by 100 times 1.5 radians per second. This would be 0.15 meters per second. So if we have two different velocities for two different wheels, two different distance wheels, how do we find the longitudinal velocity? So what exactly is this longitudinal velocity? So the longitudinal velocity would be the velocity with which the robot travel with respect to its local x-axis. So if a body fixed frame is fixed at its most convenient location, maybe for instance, consider its center of gravity or centroid, the velocity at which the robot moves along its local x-axis is its longitudinal velocity, and the robot, the velocity at which it would travel along its transverse direction would be it's a transverse velocity. That those are denoted by uv and r. So how do we approach this? So if we simply consider the left wheel alone, if we, for the time being, if we forget the right wheel, if we simply consider the left wheel, and the right wheel being stationary, so what would be the velocity of the point at which the frame B is attached? So if this point is B, if the point at which the body fixed frame is attached is B, and if we only know the left side wheel velocity V left, then what would be the velocity of the robot at B frame? Right. So the answer would be, if the contribution is only regarding the left wheel, it would be simply velocity of B some angular velocity. So if we are only considering the left wheel, the angular velocity would be in clockwise. The robot's rotation would be in clockwise direction. So velocity of B would be velocity left side wheel velocity plus some angular velocity of the robot. Let us assume that to be r times the distance between the body frame B and the extreme left position. Let this distance be B, so that the entire width of the robot would be 2B. So since if we are only assuming the left side wheel velocity, and since it is the only velocity, for the time being we are not considering the right wheel velocity. If only the left wheel velocity would be existing, velocity of V would be velocity of left minus the contribution of this angular velocity, some angular velocity r times r times the distance B. So what would that be? So we have already found out this angular velocity. Now considering only left wheel. Now, if we consider that the velocity of the left wheel is 0, and if only the right wheel is having a velocity, then what would be the velocity of the body frame wheel? That would be V right plus r times B, r cross B, omega cross B. So this would be considering only V right. So what would be the velocity of the body frame? That would be the superposition of both of these two cases. So in that case, it would be, so if we simply add these two equations, if we simply add equations 1 and equations 2, we would simply superimpose the condition where only the left wheel velocity would be existing, or the second case where only we would consider the right wheel velocity. So if we simply superimpose these two above cases, then velocity of B would be velocity of left plus velocity of right divided by 2. It would be simply, we are simply summing these two equations to eliminate the angular velocity terms. So in that regard, we have already determined what are V left and V right. So in that regard, it would be simply 0.15 plus 0.05 divided by 2. That would be 0.1 meters per second. I hope we are clear in this regard. I hope my screen is visible. So do I need to explain this once more if the concept is not clear? So in short, we are simply considering a superposition of the case where only the first wheel, only the left wheel velocity would be existing. Yeah, one second. I hope you can't my screen is not visible as, yeah. Yeah, from the next question onwards, I'll keep that in mind. I think our screen's, yeah, screen's location is not. So I'll roughly explain it once more, the question. So V left would be A times omega left, split 10 by 100 times 0.5. Is it visible? Like I suppose you can't see my screen. One second. Okay. So V left would be 0.05 meters per second, and V right would be A times omega right. This would be 10 by 100 times 0.15. This would be 0.15 meters per second. Sorry, it's 1.5, right? All right. So the linear angular velocity U would be simply a superposition of the case where only the left side wheel velocity would be existing, and the second case where the right side wheel velocity would be existing. So the linear velocity of the frame, the longitudinal velocity of the robot along its x direction, or its longitudinal velocity, would simply be the average of V left plus V right. So in this case, it would be 0.15 plus 0.05 by 2, which in essence is 0.1 meters per second. So your correct answer would be 0.1 meters per second. Is that clear? From the next question onwards, I'll keep in mind regarding the screen issues. So if you have any doubts, please let me know. So the answer is indeed 0.1 meters per second. So yeah, moving on to the second question, it says, hang on one second. Yeah, moving on to the second question. It says in a two fixed wheel differential drive mobile robot, the left side wheel angular velocity is 1.5 radians per second, and the right side wheel angular velocity is 0.5 radians per second. Both of these wheels are same size, and the wheel radius is 10 centimeters. The wheels are placed along y-axis of the body and equal distance from the body frame. The distance between the wheels, wheel to wheel along y-axis, is 40 centimeters. What will be the angular velocity R of the robot with respect to the body? So as per the question, we have been given with some data, which are we have been given a left side wheel angular velocity. So if we consider this to be left side and this to be the right side, we also have a body fixed frame attached, X and Y. This is the body fixed frame. So we are given some data that are omega left, that is 1.5 radians per second, and omega right, that is 0.5 radians per second. We have also been given the wheel radius A, that is 10 centimeters or 10 by 100 meters. We have also been given the wheel-to-wheel distance along the y-axis. So the wheel-to-wheel distance along the y-axis. that is 40 centimeters. So our question is, we have to find the angular velocity of the robot with respect to the body frame. So how would we find the angular velocity? So again, we would have to consider the principle of superposition. So if we only consider the left wheel to be rotating and the right wheel to be stationary, what would be the case? So if only left side wheel is rotating, yeah, if only the left side wheel would be rotating, how would we find out the angle? What would be the case in this case? So first we'll determine the linear velocities. V lefts would be A times omega left. This would be 10 by 100 times 1.5. So what that would be? 0.15 meters per second. And we'll consider V right when we are considering the other case of superposition. So if only the left side wheel would be rotating, what would be the angular velocity of the body fixed frame? What would be the angular velocity of the body fixed frame? So that would be omega. Let the angular velocity of the robot be omega p. We are required to find out what this would be when only the left side wheel is rotating and the right side wheel would be 0. So in this case, this would be velocity v left divided by velocity of the wheel divided by the radius. If this is the case, if only the left side wheel would be rotating. So what that would be? This would be 0.15 times 40 by 100. This would be minus 0.3750 radians per second. I hope you understood the logic, because if only the left side wheel would be rotating, this is how the velocity triangle would look like. This is the left side wheel. This is the right side wheel. So the velocity at the right side would be 0 and the left side would be v left. So it would decrease linearly all the way to 0 at the right hand side. So in this regard, what would be the velocity of the wheel? Velocity at the midpoint, at where the V frame is located. That would be the velocity of wheel velocity by 2, right? That would simply be, this distance would simply be velocity of the linear velocity would be V left by 2. So if we are dividing this linear velocity by the radius, V by R, we would get omega P, right? If VB is simply V left by 2, then what would be omega B? That would be VB by R. So R in this case would be simply half of this distance of this robot chassis. So in this regard, VB omega B in the first case would simply be minus 0.3750 radian per second. So what would happen if only the right side wheel is rotating? If only, I hope you also understood the logic behind the negative sign over here. Because if only the left side wheel velocity is existing and the right side wheel velocity is 0, the robot would move in a clockwise sense. So we would consider the clockwise sense rotation would be negative. So in the other case, when only the right side wheel velocity is existing, Right side wheel is rotating. So V right, what would be V right? V right would be A times omega right. That would be 10 by 100 times 0.5. This would be 0.05 radians per second. I hope my screen is still on. You can interrupt me using your audio or using your mic if you're facing any issues, if you are finding any issues regarding my audio, visual, or screen. All right, so we have found out our right side wheel velocity also. So in this regard, if only the right side wheel velocity is existing, how would the velocity triangle look like? This would be the right side, and the left side wheel velocity is 0. And the velocity of the body frame at point B would be simply uh, half of this V right. So again, V would be half of V right by 2. This would be velocity of V. That is, since it is basically located at halfway point around. Okay, it says my voice is breaking. Is it fine now, as of now? Atul, can you confirm? Okay, all right. Please interrupt when you feel that my voice is breaking. You can use your microphone also. So I might not be looking at the screen all the time. So I might miss your messages. So yeah, velocity VB, or velocity of the body frame with respect to the right wheel, simply be half of velocity of the right wheel. So in this regard, it would be simply half of V right. Then if that is the case, then what would be omega V? Omega V would be simply velocity of B divided by the radius RB. This would be 0.05 times 0.05 is simply the wheel velocity, 2 times 20 by 100. Where 0.05 is the V right. So V right by 2 would be VB actually. V right by 2 would be VP, and 20 by 100. 20 centimeters is the distance between the body frame and the right frame, the right wheel. So in this case, the final answer would be 0.1250 radian per second. And again, since only the right wheel is rotating, the sense of rotation would be counterclockwise. So that would mean that the sign, as per the sign convention, since we are rotating counterclockwise about the z-axis, it would be a positive rotation. So superimposing these two results, yeah, we would get omega b as minus 0.25 radians per second. Superimposing these two results, we would get the angular velocity of the robot's body as 0.25 radians per second. So our answer would be option A, 0.25 radians per second. So there is also one another way. You might have already studied the wheel transformation matrix. So if you simply substitute all these values in that wheel substitution matrix, you would still get the right answer. So in case of a differential robot, what is your wheel transformation matrix? So in the case of wheel transformation, differential wheel drive, your wheel transformation matrix is simply, W would simply be A by 2, 0, 0, minus A by 2D, A by 2D. All right. where A, I hope I have, as per the convention, it is already clear what A and what D are. So A would be the wheel radius, and D would be the distance between the wheel to wheel distance. So if we simply plug in these values, where A is simply, yeah, A is 10 by 100 meters, and D is 40 by 100 meters. So I hope as per the wheel transformation matrix, you know the transformation zeta is W omega, where zeta, yeah, zeta would be W times omega, where zeta is your UVR, where U is the velocity along x-axis, V is the velocity along y-axis, and R is the angular velocity about the z-axis. All of these are with respect to the robot's body fixed frame. And your omegas are also given. Your omega 1 is 1.5 radians per second, and omega 2 is 0.5 radians per second. So if you simply plug these relations in this transformation, you would still end up as, you will end the third element of zeta. Zeta 3 would be 0.25, minus 0.25 radians per second. I hope that is also clear. You will still end up with the zeta values. You will apart from that, you will also get u, v, r also. If you simply substitute all these values, the angular velocity values and the wheel transformation matrix, the geometric parameters regarding the wheel transformation matrix, you will still get the correct answer, minus 0.25 radians per second. Either way is fine, no problems. So I hope this is clear. If you have any doubt, please ask. Please let me know. Yeah. So the answer is indeed 0.25 radians per second. Okay. So moving on to question 3. Hold on 1 second. Moving on to question 3, it says if the number of controllable degrees of freedom is equal to the total degree of freedom, then the system is called as a, can you answer? Atul, if you can answer the correct answer. Can you answer this question? If you can hear me. Okay, all right. So if the controllable degrees of freedom is equal to the total degree of freedom, so in case of a mobile robot, a brief idea would be, in case of a mobile robot, you would require 3 degrees of freedom. So if this is the frame that is fixed around the earth, or if this is the inertial frame, and this is the chassis of a robot. Yeah, this is X, capital X and capital Y. This is small x and small y. This is a body fixed frame. So a degree of freedom for this robot would, the definition would be the number of variables to fully define the configuration of a mobile robot. So how many variables would you require to fully define the configuration of a wheel mobile robot? You would require 3 variables, right? 2 variables for position. So if this is the robot's frame, you would require 2 positions, X and Y, and 1 more variable, psi, to determine its orientation also. So if the robot is oriented in some fashion along the plane, you would require two positions to determine its center of gravity, to determine its centroid point, and also one more variable psi to fully identify its orientation also. So in that regard, you would require a minimum of 1 second. I think I'm having some connectivity issues. Yeah. Yeah. So in this regard, you would require at least three variables. You would require at least three variables to fully specify the configuration of a wheel mobile robot. And the number of controllable degrees of freedom means the number of inputs or the number of, the number, in a sense, the number of controllable inputs that we can give to a robot. So if the number of controllable inputs is equal to the degree of freedom, so if the number of controllable inputs is at least equal to the total degrees of freedom of the mobile robot, then the mobile robot is called holonomic. It's a basic definition of holonomic system. So just by looking at the constraints also, you can see where you can identify whether the robot is holonomic or not. So in this regard, if the number of controllable inputs is at least equal to the number of degrees of freedom of the robot, then the robot is said to be holonomic. All right. So the answer is indeed holonomic. The robot is called a holonomic robot. Yeah. Again, a similar question. If the rank of the wheel configuration matrix of a wheeled mobile robot is less than 3, then the system is called mobile robot, holonomic robot, non-holonomic robot, differential drive, structure, manipulator. So in this case also, it's a clear-cut definition regarding what is a holonomic robot. All right. 1 second. It says my connection is breaking. Let me try and switch to a different connection. So I apologize for the interruption. I suppose that it is not a problem that is not in my control. Please bear with me, and I'll be happy to repeat if the problem persists. Please let me know if the problem persists. So again, regarding the question 4, if the rank of the wheel configuration matrix of the mobile robot is less than 3, then the system is called a mobile robot, a holonomic robot, a non-holonomic system, a differential drive, a structure, and a manipulator. So it's just the inverse of whatever problem that we have discussed earlier. So in this regard, the answer would be a non-holonomic robot. So if the number of controllable inputs are basically the wheel configuration matrix. So wheel configuration matrix is something that map the system parameters U, V, R. We use the wheel configuration matrix to map the system parameters to the number of controllable inputs. So if the rank of the wheel configuration matrix is less than 3, that would essentially mean that we have lesser number of controllable inputs than the number of degrees of freedom that we are trying to control. So in that regard, the robot that have a wheel configuration matrix having a rank lower than 3 would come under non-holonomic robots. So the correct answer is non-holonomic systems. So again, I hope the reasoning is clear. It is straightforward from the lectures also. All right. So question 5. Yeah. So question 5, we straight away deal with the wheel configuration matrix. So for a given mobile robot with 4 mechanism wheels, the wheel configuration matrix is given as, this is a standard wheel configuration matrix of a 4 mechanism wheel drive. If the robot is to move in a lateral direction, upwards, so the direction and the sense of direction is also given, then what will be the right combination of these wheel angular velocities? So as per our course, the configuration of the wheels of a mechanical wheel drive is somewhat similar to like this. We have a robot chassis. So each of these mechanism wheels will have passive rollers along these directions. And as per our convention, we would consider this to be the first wheel. We would consider this to be the second wheel, and this to be the third wheel, and this will be our fourth wheel. I'll also attach a frame of reference, a body fixed frame of reference, X axis and Y axis. And again, the wheel configuration matrix is also given. Wheel configuration matrix, W would be 1, 1, 1, 1, 1 minus 1, 1 minus 1, minus 1 by D minus L, minus 1 by D minus L, 1 by D minus L, 1 by D minus L. So we should be knowing that, the transformation zeta would be W times omega, where zeta is UVR. I hope we know what UV and R are, where U would be the linear velocity along the x-axis of the body fixed frame. V would be the linear velocity of the robot along the y-axis, and R would be the rotation about the z-axis along the plane. So all these values, U, V, R are basically instantaneous because it is represented with respect to the body frame. So all these parameters are instantaneous at a particular instant. And we are also given an omega matrix, we would need to find what are these combination, right configuration of this omega, so that the robot will move in the lateral direction. So I hope you have no trouble in identifying what is lateral direction and what is longitudinal direction. So if this is the robot's frame, the lateral direction is this. This is your lateral direction, and this is your longitudinal direction. And you would want the robot to move upward along the lateral direction. So in this regard, what is the right combination of angular velocities? So in essence, you would require zeta to be 0, 1, 0, or maybe 0, k0. You would only expect a zeta matrix such that it should only have a component along the v component. All the other components should be 0. So that means the robot can only have one velocity along the lateral direction. All the other two components should be 0. That is what the question is asked. So what would be the right combination so that it would give zeta 0, k0? So we'll take a look at each of these cases. What would we get if for the first case, omega 1 is omega, omega 2 is also omega, omega 3 is omega, omega 4 is omega. If we are giving equal angular velocities in equal directions for all the four wheels, how would the robot move? So if you cross multiply this case, what would be the case? The first row would be some constant a by 4 times 4 omega, right? So again, the first component itself is giving some velocity along the longitudinal direction. So we can straight away we can rule out that example. We don't have to even expand the matrix multiplication any further. Then what about the second case? The second choice. Second choice gives you minus omega, minus omega, minus omega, minus omega. Again, it should be obvious that we have simply inverted the direction of the angular velocities. So again, the first component, if you consider the matrix multiplication, the first row would be some a by 4 times minus 4 omega. It will be some 4 omega. Again, that is not the requirement that we want. We would want the first and the third variables to be 0, and only the second variable should be non-zero. So what about the third case? What about the third option? The third option would be first wheel angular velocity is omega, the second would be minus omega, third is omega, and the fourth is minus omega. So if you try and multiply this out, what is the end result? So the first column would be some constant a by 4 times minus omega, sorry, this is plus omega, right? In the third instance, the first angular velocity is plus omega, minus omega, plus omega, minus omega. So the first row would be 0. And what about the second row? It would be omega, plus omega, plus omega, plus omega. And the final row would be, minus omega by d minus L, plus omega by d minus L, omega by d minus L, minus omega by d minus L. So in the third case, the first row would be 0. The second row would also cancel out. Minus omega plus omega cancel out, minus L plus omega minus d minus L cancel out. Again, the first row also cancel out. We'll only end up with some 4 omega value and again a constant of multiplication. So this is as per our requirement. The velocity along the longitudinal direction is 0, and the rotational angular velocity is also 0. We only have a non-zero component that is only along the lateral direction. So in this case, the third answer is indeed correct. We don't even have to check out what are the other cases also. So I hope this is clear. It is simply a matter of matrix multiplication. We are required to find out the right combination of wheel angular velocities so that the robot will only have, so that the robot will only move in a lateral direction in upward sense or along the positive y-axis. So I hope this is clear. Please let me know if you have any questions. Apologies if the audio visual is breaking. Yeah, so the answer is indeed correct. Option 3 is the correct option. If the first angular velocity is positive, the second is negative, the third is positive, and the fourth is negative, the robot will simply move. Yeah, Atul has said it one more time. I need to explain it one more time. So no problem. I can explain it, no problem. So I'll start with the question. It says for a given mobile robot with 4 mechanism wheels, the wheel configuration matrix is given as this one. And if the robot is to move in a lateral direction upward, then what will be the right combination of the wheel angular velocities? So yeah, as per the question, we have been given a requirement that the robot should only move upward. It cannot move in any other direction. So as per the transformation matrix, you will have a robot transformation matrix that relates the joint rates with respect to the control inputs, W times omega. So in this regard, what is this zeta matrix? Zeta would be simply your vector of U, V, R. So this is mapped onto the wheel angular velocities by this W matrix that is given in the question. Omega 1, omega 2, omega 3, omega 4. So this W matrix is already given in the question. This is your W matrix. And you are required to find out what is the right combination of this so that you would get a desired zeta vector. So in this regard, the question asks say. Yeah. We are required to find out the right combination of wheel angular velocities if the wheel transformation matrix omega is given. And as per the question, it says the robot should move in lateral direction upwards. So how would this zeta matrix or the wheel velocity vector, the robot velocity vector would look like? It would look like 0. It'll have some component along the V axis and it will have 0 component along the R axis. So we are required to find out what is the right combination, what are the right combination of wheel angular velocity so that we'll get zeta. This is the zeta vector. So we'll get the zeta as per our requirement. So in this regard, what is your wheel configuration matrix? This should be A by 4 times 1, 1, 1, 1, 1 minus 1, 1 minus 1, minus 1 by d minus L, minus 1 by d minus L, 1 by d minus L, 1 by d minus L. So if we simply take a look at the third option, sorry, where omega 1 is omega, omega 2 is minus omega, omega 3 is omega, omega 4 is minus omega. If we substitute it as omega minus omega, omega minus omega, and if we multiply this throughout, what would be the case? Omega minus omega, omega minus omega would be the first row, and the second row would be omega plus omega plus omega plus omega, and the third row would be minus omega by d minus L plus omega by d minus L. Then omega, I think the third, yeah, omega by d minus L minus omega by d minus L. So the first row basically cancels out omega minus omega, omega minus omega. There is also an a by 4 over here. And the second row would be some a times 4 omega by 4. And the third row again cancels out minus omega by d minus L plus omega by d minus L plus omega by d minus L minus omega by d. So the robot will only have a velocity along the v axis. So this is what the question asked. This is what the question asked. So I hope this is clear in this regard. It has zero velocity along the u direction. It has zero velocity along the r direction. It only has velocity along the v direction, v component. Or in other words, the lateral component. That is what the question asked. That is what the question asks. Okay, all right. Thank you. So that is indeed the correct answer. The option 3, omega 1 is positive, omega 2 is negative, omega 3 is positive, omega 4 is negative. So yeah, moving on to question 6. It is also regarding a mechanism wheel mobile robot. So I hope we can simply copy this diagram. It might come useful in our next problem also. Yeah. So in this question, what it asks is that for a given mobile robot with 4 mechanism wheels, the wheel configuration matrix is again the same, what the same thing that we discussed in the previous problem. If the robot is to rotate in a counterclockwise direction upward, then what will be the right combination of these wheel angular velocities? So if this is the robot, if the robot should stay at this exact location, and if it should rotate counterclockwise along this axis, it shouldn't move. It should be fixed at this axis, and it should rotate in the counterclockwise sense. Then what is the right combination of wheel velocities? So again, you are given the zeta vector, and as per the question, it says the zeta is basically counterclockwise rotation upward. It doesn't have any component along its x-axis and its y-axis. So zeta is given as 0, 0, some constant k along the r direction. U, V, R. I hope you are familiar with these terms from a course. U is the velocity along x-axis. V is the linear velocity along the y-axis, and R is the angular velocity of the robot about the z-axis, and the rotation is planar. So as per the question, we should interpret the question such that our zeta vector is 0, 0, k. It says the robot should rotate in counterclockwise direction, so that our zeta vector would be 0, 0, some constant, some positive constant. As a robot is rotating about the positive, in counterclockwise direction, the rotation is about positive z-axis. So our vector should be 0, 0, k. And how is this, how is this zeta vector related to the angular velocities? Zeta vector is related to the angular velocity is using this relation. Zeta would be omega times omega, and sorry, W times omega, where W is the wheel configuration matrix. And we have also been provided with the wheel configuration matrix. So we'll try out each of these options. Options, we have been given options 1 to 5. We'll try out each of these options. So I'll write the wheel configuration matrix. I'll write out this wheel configuration matrix. It is wheel configuration matrix is A by 4 times 1, 1, 1, 1, 1, minus 1, 1, minus 1, minus 1 by D minus L, minus 1 by D minus L, 1 by D minus L, 1 by D minus L. So if we start with the first option, what does the first option say? It says the first wheel angular velocity, all the four angular velocities, wheel angular velocities are respectively omega 1, omega, 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 omega. If all four wheel angular velocities are exactly the same in the exact same sense of rotation, then if we simply multiply out these matrix and vectors, what will we get? The first row would be some A by 4 times 4 omega, right? Times omega plus omega plus omega plus omega. It would be 4 omega. Again, like this is again the first row is non-zero. This is not the case we want. We want the first two rows to be 0, and it should only have a non-zero component at the third row. So if we simply use the first case, first of these options that we have, if we multiply it throughout, what we are getting a non-zero first row itself. So that is not the case that we require. So we don't even need to consider any further cases. We can simply eliminate that to be the correct case. So what about the second case? Second case is the first angular velocity is minus omega, second is minus omega, third is minus omega, fourth is also minus omega. Again, all four angular wheel velocities are of the same magnitude, but of different direction. It will be similar to the previous case, but the sense will be opposite. The direction will be opposite. So in this regard, again, we'll get some value, an exact identical value as the previous case, but the direction would be negative. That's all, some 4 omega. Again, we have a non-zero value at the first row. We don't need to evaluate what the second and third rows. Then we'll try with the third case. What is the third case? It is omega minus omega, omega minus omega. We'll see if this is identical to, this case. This is our requirement. So, if we multiply it throughout, we'll take this A by 4 as common. If you multiply it out, what would be the first row? It would be omega minus omega plus omega minus omega. And the second row would be omega, again plus omega, minus and minus cancels plus omega. Again, we have a non-zero second row. Again, that is also not the correct answer, but yeah, we'll proceed it anyway. The third row would be minus omega by d minus L, omega by d minus L, omega by d minus L. This is plus, again minus omega by d minus L. So this and this cancel, this and this cancel. In the first row also, this and this cancel, this and this cancel. So our answer would be A by 4 times 0, 4 omega 0. Again, this is not the case we want. We want the non-zero element to be at the third row. But here in this case, we have a non-zero element at the second row. Clearly, this is not the case that we require. And this being the third option, we'll consider the fourth option also. What does the fourth option say? So as per the fourth option, the combination is minus minus omega, minus omega, omega, omega. And if we multiply this out, it would be minus omega, plus omega, plus omega, some a by 4 times. And yeah, the second row would be minus omega plus omega minus, sorry, where were we? Yeah, sorry. Let me rewrite this. Yeah, the fourth case is minus omega, omega. So multiplying this out, what would we get? It would be minus omega, plus omega. The second row would be minus omega, plus omega, minus omega. And the third row would be omega by d minus L, omega by d minus L, omega by d minus L, omega by d minus L. So again, the first row, minus and plus cancels, minus and plus cancels, minus plus, minus plus. Third row, we'll have all pluses. So it'll be a by 4 times 0, 0, 4 omega by d minus. So this is exactly similar to the form that we want over here. So in this regard, we can confidently say that option 4 is the correct answer. Option 4, this is the correct answer. I hope this is clear. We have been in the question, we have been given our requirement, the robot should move in a counterclockwise direction. And we are supposed to find out the right wheel angular velocity configuration. So in this regard, we have tried each of these cases that would give you the final solution in this form. So it turns out that the wheel velocity combination minus omega, plus omega, and plus omega is the right combination. That would give you the zeta vector of the form 0, 0, some constant at the third entry. All the other entries are basically 0. So I hope in this regard, this is clear enough. Okay. I think we made a mistake somewhere. I think I have made a mistake in this option. As per the, yeah. Option 4 should be the correct option, not option 6. Option 4 is the correct option. Minus omega, okay, 1, 1. Okay, one thing that you should be very careful is that, see, we have made a mistake actually. So the answer is indeed option 6. So as per our answer, it is a by 4 times 0, 0, 4 omega by d minus L. So yeah, this, one second. This case will only be true if d is greater than L. Otherwise, this entire term would be negative. This entire term would be positive if and only if this condition is satisfied. So what happens if L is greater than D? If L is greater than D, then this term would turn out to be negative. The final term would turn out to be negative. So in the question, it doesn't specify anything. It doesn't actually specify anything. So as per the convention that we have used in our textbook, the width-wise dimension is termed as L. This would be 2 times D, and this would be 2 times L. This would be 2 times L, where L would be length and D would be the depth. And if nothing is specified in the question, if nothing is specified in the question, you should always assume that L would be greater than D, because obviously the length of the chassis would be greater than the depth of the chassis. So in most of the cases, you should always assume, even if it is not explicitly specified in the question, you should always assume that L is always greater than D. So in this regard, whatever value you would get in the final answer would be a negative quantity, because if you consider L to be greater than D, the final entry would be negative, because it says D minus L. So if L is greater than D, you would get a negative value. So we would, in the question, we would want the robot to rotate in a counterclockwise direction. So we have to ensure that the third entry should be positive. So the fourth option is not correct. It's not omega, it's not, minus omega, plus omega, plus omega. We should reverse the sign. It should be omega, omega, minus omega, minus omega. It should be the sixth option as per the solution key. I'll solve this just to prove this fact. So again, the wheel configuration matrix is already here. So as per the sixth option, if you are simply changing the wheel velocity direction, it says omega 1 is omega, omega 2 is omega, omega 3 is minus omega, omega 4 is minus omega. If you multiply this out, the first entry would be omega plus omega minus omega minus omega. This cancels out to be 0. The second row would be omega minus omega plus, omega minus, again, the second row would be omega minus omega minus omega plus omega, and the third entry would be minus omega by D minus L, minus omega by D minus L, minus omega by D minus L, minus omega by D minus L. So the first term cancels out to be 0. So the first row cancels out to be 0. The second row also cancels out to be 0. And the third row we'll get minus 4 omega times D minus L, sum A by 4 times. So in this regard, if L is greater than D, this term would be positive. Don't be fooled by the negative sign there. If we consider that L is greater than D, even with the minus sign, the entire quantity would be still be a positive. Because D minus L is a negative term, we also have a negative at the top. So both of this negative will get cancelled out, and we'll end up with a positive value for the third row. So that is our requirement. We'll want a positive constant at the third entry, at the third row, so that the robot will rotate along the counterclockwise direction. So I hope this is clear. We shouldn't be fooled by the negative sign at the numerator, because the denominator is B minus L. So if L is considered to be greater than D, if the length of the robot is considered to be greater than the depth or the width of the robot, then D minus L would always be a negative quantity. So the negative and negative will get cancelled. We'll end up with a positive quantity. So option 6 is the correct choice. I hope that is clear. And please excuse if the audio is still breaking. I can explain this to you again if the concept is not clear. So option 6 is indeed the correct choice. So yeah, now we'll move on to option 7. Again, it is a question regarding a wheel configuration matrix, but for a different configuration, called omnidirectional wheels. So what is this omnidirectional configuration? So briefly recreating the convention that we are using in our course, we have three sets of wheels aligned in 120 degrees apart. Sorry. Okay, 120 degrees apart. So as per the convention that we follow in our course, this is the first wheel, this is the second wheel, and this is the third wheel. And the body fixed frame would be at the center of the chassis. And this would be the x-axis, this would be the y-axis. The velocity along the x-axis is called u, the velocity along the y-axis is called v, and the rotation along the z-axis is called r. So the question says, for a given mobile robot with 3 omnidirectional wheels, the wheel configuration matrix omega is given so and so. If the robot is to move in a lateral direction upward, then what will be the right combination of these wheel angular velocities? So again, I hope we don't have any confusion regarding what is lateral and longitudinal direction. So along this x-axis is what we call the longitudinal direction. And along the y-axis is our lateral direction. And our question says the robot should move in the lateral direction upwards. It should not have any rotational component. It should not have any longitudinal component. It should only have a lateral direction. So our zeta matrix, our UVR vector, in fact, should look something like 0, a constant k, and 0. It should only have a component along the lateral direction. So this is how our zeta vector should look like. And how is this zeta vector related to the vector of wheel angular velocities? Zeta is related to wheel angular velocities using the wheel configuration matrix WW. So yeah, so we have been given a wheel configuration matrix. So I'll take out this a by 3 term outside. A by 3. If I'm taking this a by 3, how would the matrix look like? It look like 0 minus root 3, 2 minus 1, minus 1. Then we would have an a 1 by L component. Third row, 1 by L, 1 by L, and 1 by L. We will evaluate each of these options one by one. So the first option says all the angular velocities for all the 3 wheels are omegas. So if this is the case, what would be the first row would write? First row, if you multiply this out, it would be simply minus root 3 times omega plus root 3 times omega. So the first row is essentially 0. We'll also have an a by 3 outside. And the second row would be 2 omega minus omega minus omega. And the third row would be omega by L plus omega by L plus omega by L. So this is evident that it will look somewhat like 0, 0, 3 omega by L. So only the third row is non-zero. All the other rows are non-zero. But according to the question, we would want only the second row to be 0 and not the third row. So obviously the first option is not the correct one. So then what about the second option? The second option says all the three angular velocities are omega, but in the negative direction. Again, obviously, it should be evident that that is also not going to be the case, because we'll end up with the same case that we solved before, but with the negative direction. It'll be like 0, 0 minus k, what we solved earlier. That is not our requirement. Our requirement is we should be obtaining our zeta vector like this. Only the second row should be 0 as per the question. Then what about the third case? What is the third case? Third case would be omega minus omega by 2 minus omega by 2. So if we expand this out, a by 3 times first element would be 0 minus plus root 3 omega by 2 minus root 3 omega by 2. And the second row would be 2 omega plus omega by 2 plus omega by 2. And the third row would be omega by L minus omega by 2L minus omega by 2L. So if you simplify this out, how will this look like? These two terms cancel. Sorry. Again, I'm making the same mistake of going out of the window. Yeah. So if we simplify this out, it will be like a by 3 times 0. And the second, it is, yeah, half 1. So 3 omega. And the third column basically cancel. We'll have negative half and negative half, that is 1. And this is positive 1, so that also cancels out. So it is similar to the case that we require a 0 in the first row, a constant in the second row, and 0 in the third row. So this is what the question asks. It should only have a lateral direction upwards. So the right answer should be the angular velocity omega 1 should be omega, and omega 2 should be minus omega by 2, and omega 3 should be minus omega by 2. So if the first wheel is having an angular velocity omega and the other two wheels have negative half omega, then the robot will move vertically upward in the lateral direction. So as per the question, the right answer would be option 3. So I hope this is clear. Please let me know if you need any further clarifications or if I need to explain this any further. I hope it's clear. Yes, so as per the key, the answer is option number 3. Yeah, and moving on to question number 8. Again, this is mostly related to holonomous robot and non-holonomous robots. One second. Yeah, again, the question says for a given land-based robot, for a given land-based mobile robot, the wheel configuration matrix is given as W and M greater than N. So what does that physically imply? So we know the relation between that maps the zeta vector, the vector of angular velocities in the robot's frame, is W times omega. So this is a system of linear equations. So what does M greater than N means? So this simply means that number of rows is greater than number of columns. So again, this means that our W matrix would be a kind of a tall matrix. So one example I would give, zeta would be obviously 3 cross 1 because it has UVR components, and omega would only have 2 cross 1. In case of a differential robot, if we consider a differential robot, it will have only 2 values for omega 1 and omega. Then what would this W matrix look like? It'll be like a 3 cross 2 matrix, right? Zeta would be a 3 cross 1 matrix, W would be a 3 cross 2 matrix, and omega would be a 2 cross 1 matrix. So if m is greater than m, this W matrix would be a tall matrix. Number of rows would be greater than number of columns. So as per the linear algebra theory, if number of rows is greater than number of columns, what do we have? If the number of rows is greater than number of columns, we have an overdetermined system. An overdetermined system. Or in the sense, number of equations is greater than number of unknowns. I hope this is clear. So what happens if this is the case? If the number of equations are greater than number of unknowns, we'll have no solutions, right? We'll have no solutions. That is not the case when number of equations are equal to number of unknowns, or if the number of equations is less than number of unknowns. So if the number of equations were less than number of unknowns, we will have infinite solutions. But if the number of equations are greater than number of unknowns, we have no solutions. So we would not be, if zeta is given, how would we find omega? If both were equal, if m were equal to zeta, we would simply use the inverse matrix, right? W would be omega inverse zeta. But since in this case, W is not a square matrix, in order for us to take inverse, we would require W to be a square matrix. But in case of these cases, in case of when m is greater than n, it's obviously going to be a rectangular matrix. It's not going to be a square matrix. Then how would we find out the solution omega? Well, in fact, if this is indeed the case, there are no solutions. As I have already said, there are no solutions, but there is a shortcut for this. We can find an approximate solution. Omega, this is basically an approximate solution, such that the error between theta minus W omega star is the approximate solution. So the distance or the norm or the least square error between the zeta vector and W times omega would be minimal. And whatever we find as omega star is not an exact solution. It is only an approximate solution where the least square error is minimal. Least square error is minimal. So how would we find this least square error? Least square error for a vector would be zeta minus omega transpose theta minus, W omega. So this would be a 1 cross 3 matrix. This would be a 3 cross 1 matrix. So if you multiply this out, this entity would in term, let us call this as a Lagrangian. We would want to minimize this function so that whatever omega we get out after minimizing this function would be the approximate solution. So if we simply multiply this out, what will we get? Zeta transpose minus W omega transpose W transpose zeta minus W omega. All right. If we multiply this out, what will we end up with? If we multiply this out, we'll get zeta transpose zeta minus zeta transpose W omega minus omega transpose W transpose zeta plus omega transpose W omega. This would be our L, Lagrangian function. So if you want to find out the value that will make the least square error minimal, we need to find out, we need to differentiate this Lagrangian dou L by dou W. We should make this 0 and we should find out what value would minimize the least square error. what value would minimize the least square error? All right. So if we differentiate with respect to omega, the first term, if we differentiate this term with respect to omega, what will we get? It will be, the first term would be 0 because as there are no omega terms, it will be 0. And the second term would be minus zeta transpose W omega. We are differentiating this entire equation with respect to omega. And the third term would be omega. Yeah. The third term would be, one second, zeta transpose omega. Third term would also be zeta transpose omega. One second. Minus of, yeah, minus zeta transpose omega minus omega transpose zeta plus yeah, 2 omega transpose omega. Sorry, I'm confusing with myself with W and omega. 2 W transpose W omega. If I differentiating. So what if we check out these dimensions? So zeta transpose would be 1 cross 3, and W would be 3 cross 2. So this is 1 cross 2. And W transpose would be 2 cross 3, and zeta would be 3 cross 1. So this is indeed 2 cross 1. So to correct out these dimensions, it should be the opposite. It should be yeah, it should be zeta transpose omega. Then only we'll be able to have consistent dimensions. And the other case would be 2 times 2 cross 3, 3 cross 2, and 2 cross 1. This would be 2 cross 1. Again, to make the dimensions consistent, it should be yeah. To make the dimensions consistent after differentiation, we would end up with this term 2 omega transpose, sorry, 2 omega W transpose W. So dimensions would be 2 cross, what are our dimensions? So this will be omega transpose, yeah. 1 cross 2, 2 cross 3, 3 cross 2. So we will end up with again 1 cross 2. Also, all these are 1 cross 2. So this entire, if you are equating this entire term to be 0, we'll get 2 omega transpose omega would be zeta transpose W. 2 zeta transpose, because these are basically the same. So if we solve this out, if we again take the transpose in both sides, what will we get? If we take the transpose, what will we get? It will be like omega transpose, I hope it is clear, omega, sorry. It'll be W transpose W omega would be omega, sorry, W transpose zeta. And what would be W? W would be W transpose W inverse W transpose zeta. And this is what we call as the pseudo inverse W plus. And in this instance, it's called a left pseudo inverse. So in the case when M is greater than N, we'll have this condition. This is how we determine the pseudo inverse when M is greater than N. And remember the value of omega in this case. This is not an exact solution to the problem, zeta minus W omega. This is an approximate solution where the least square error would be minimal. And again, what are the conditions? So in order for this to exist, in order for the left pseudo inverse to exist, since this is an inverse, since W, W transpose W entire thing should inverse, and inverse should exist, then determinant of W transpose W should not be 0. It should not be 0, right? Because determinant of a matrix would be adjoint A by determinant of A, and determinant of A should not be 0. I hope that is clear. So in this regard, the inverse term W transpose W inverse, if that should exist, then determinant of W transpose W should not be 0. So if that is the case, then what is the correct answer? If M is greater than N, what would be the pseudo inverse W plus at the condition is, and what condition would it be valid? So the first option, again, that is not the correct answer, because as per the left inverse, this is not the case. It should be W inverse W should be I. And the second option, this is not correct. Not correct as per our final answer. Third option is also not correct. Fourth option, what is it? W transpose W inverse W transpose. W transpose W not 0. W pseudo inverse W is I. This is the correct answer. This fourth option is the correct answer as per our definition. So I hope that is clear. Again, this entire derivation is available at the course at the lecture videos. So how in this case, when M is greater than N, or if the number of equations is greater than the number of unknowns, we'll go with the minimization of the least square error. We'll find out an approximate solution of omega such that the least square error is minimal. So the value of omega star corresponding to the final value, omega transpose omega, the whole inverse, multiplied by omega transpose times zeta will give you the solution of omega star. That will have the least square error. Yeah, that will have the least square error as compared to the zeta vector. So yeah, option 4 is indeed the correct answer. So yeah, moving on to question 9. I think we have around a few more minutes to wind up this session. We have a matrix, rectangular matrix that has more number of rows than more number of columns. All right, more number of rows than more number of columns, exactly similar to our previous case. Then what would be the Moore-Penrose pseudo inverse? So as per the previous inverse, the Moore-Penrose pseudo inverse would be A transpose A, the whole inverse A transpose. So if you evaluate this value 0.1, if you take the transpose 0.1, 0.1, 0, 0, 0.5 minus 0.5, this is A transpose. Then A would be 0.1, 0.1, 0, 0, 0.5 minus 0.5. And this entire value, you have to take the inverse and multiply that with A transpose, 0.1, 0.1, 0, 0, 0.5 minus 0.5. You will end up with the required pseudo inverse. And in this regard, the correct answer would be, if you multiply this out, if you do this metric manipulation, end up with the first answer, 5, 0, 1, 5, 0, minus 1. This would be the correct answer. And yeah, moving on to the 10th question. Again, these are similar to the previous questions that we have discussed earlier. Again, it is in this case the transformation matrix of a mechanism wheel for mechanism wheel robot is given, and we are required to find out the combinations, the right combination of wheel angular velocities, so that the robot will move in lateral direction, but along the negative y-axis. It will move along the negative y-axis. So again, reproducing the mechanism wheel robot, it'll have a robot chassis, 4 wheels, and all the 4 wheels will have passive rollers. This is x-axis, this is y-axis. And along this is what we have, the longitudinal direction, and along the y-axis is what we have, the lateral direction. And the velocity component along x-axis is termed as u. The velocity along the y-axis is denoted as v, and the rotation about the z-axis is r. So the zeta vector would be u, v, r. And as per our requirement, the robot should be moving in lateral direction, but in downward sense. So the robot should move in downward direction, laterally. So that's why I've drawn a lateral arrow pointing downwards. So if this is the case, then what is the right combination of wheel angular velocities? So again, just like how we did in the previous problems, I would simply take out each of these cases. A by 4 times 1, 1, 1, 1, 1 minus 1, 1 minus 1, minus 1 by d minus L, minus 1 by d minus L, 1 by d minus L, 1 by d minus L. Again, it should be considered that the dimension L should be greater than d, where L, the length of the robot is 2L and the width of the robot is 2D. And should be obviously the length of the robot should be considered greater than the width of the robot. So as per the question, our zeta vector should look somewhat like 0, minus k, 0, where minus k would correspond to lateral direction moving in the negative y-axis. So if you take out the first case, omega w, omega 1, omega 2, all are positive omegas. This obviously won't be the case, because if you multiply out the first row itself, it'll be like a by 4 times 4 omega. That is non-zero. That is not the case we want. If we consider the second case is nothing but all the directions being reversed. That would also be the correct answer, because it would be exact same as of the first option, but all the angular velocities would be all the values would be in the negative sense. So again, no point in further pursuing that option. And option 3 says it'll be omega minus omega, omega minus omega. So if you multiply this out, what will we get? A by 4 times omega minus omega plus omega minus omega. The second row would be omega plus omega plus omega plus omega. And the third row would be omega minus omega by d minus L plus omega by d minus L plus omega by d minus L minus omega by d minus L. Again, these would get cancelled. Plus omega minus omega plus omega minus omega, and the third row will cancel, and you will get something like 0, 4 omega 0. This is similar to our requirement, but we would want a negative sign also, because we are asked to find out the case when the robot moves in the downward direction or along the negative axis. So since the term is positive here, that is also not the choice that we are looking for. So moving on to further cases. So like if this is the case, we have found out the right magnitude, but we are still not correct in terms of the direction. So what happens if we simply reverse these values? If we simply invert these values, the first one would be negative, second would be positive, third would be negative, and fourth would be positive. We'll simply try this out. So the first row would be minus omega, plus omega, minus omega, plus omega. The second row would be minus omega, minus omega, minus omega, minus omega. And the third row would be omega by d minus L minus omega by d minus L minus omega by d minus L omega by d minus L. So on simplifying, we would get, these would all get cancelled. We will get minus 4 omega on the second row, and third row would also be 0. So this is similar to 0, a constant in negative axis, and 0. And as per our requirement, this is what we wanted. So in this case, what is the correct answer? Minus omega, omega, minus omega, omega. So this corresponds to which option? This is our correct answer. This corresponds to option 5, I guess. Yeah. So that is indeed the correct choice, option 5. And again, for the omnidirectional robot, again, a similar problem. So it says if this is the wheel configuration matrix, W, and if the robot should move in a longitudinal direction. So yeah, UVR, if you want to translate this in terms of UVR, it should be minus a constant 0, 0. Because it says it should move backward along negative x-axis. So if that is the case, then what is the right combination of wheel velocities? So we'll again try and expand this thing as zeta is W times omega, where now we'll expand this out. I'm taking a by 3 outside. This will be 0 minus root 3, 2 minus 1 minus 1, 1 by L, 1 by L, 1 by L. So if we take the first option, it says omega, omega, omega. And if we multiply this out, it's obvious that the first row is 0, but that is not the case we want. We want the first row should be a constant, or our first row should be non-empty. And moving on to the second solution, minus omega, minus omega, minus omega. Again, this is identical to the first case. The first row would still be 0, but all the other terms would be flipped. Not worth pursuing the second option also. Third option says omega minus omega by 2 minus omega by 2. So what happens if we expand this out? A by 3 times root 3 omega by 2 minus root 3 omega by 2. Root 3 omega by 2. Again, the first row becomes again the first row becomes 0, right? Root 3 omega 2 by 2 minus root 3 omega by 2. Again, this is also not the correct option because we need the first row to be non-zero. So what about the fourth case? Sorry, I think we have considered the third case. We'll go on with the fourth case. Omega, omega by 2, omega by 2. Again, this is also similar to the third case with the velocities being flipped. I also suppose it's not worth pursuing because if you expand the first row itself, you will see that it will be like 0 times omega minus root 3 omega by 2 plus root 3 omega by 2. So again, the first row is 0. Then, what about the fifth case? It will be 0 minus omega, omega. If we expand this out, what will we get? It will be 0 plus root 3 omega plus root 3 omega. Then the second term would be minus omega plus omega, and the final term would be minus omega by L plus omega by L. So this would be similar to a constant k, positive constant 0, 0. But our question specifically says it should be backward in the negative x-axis. So we would also expect a negative sign also, but in this case, we don't have a negative sign. Again, this is not, again, this is also not the correct answer. So we only have one more option to consider. The first being 0, the sixth option, first being 0, second being plus omega, and third being minus omega. If we expand this out, we'll end up with minus root 3 omega, minus root 3 omega, and second would be minus omega, plus omega. The third row would be omega by L, minus omega by L. So this would be a by 3 times minus 2 root 3 omega, 0 and 0. So this is similar to our requirement, a negative constant 0, 0. This is what as per our requirement. So option 6 is indeed the correct answer. This is the right combination of wheel angular velocities. Yeah, and one more case regarding this omnidirectional wheels. It says the robot should rotate in clockwise direction, negative rotation about z-axis. Negative rotation about z-axis. So our zeta vector would look like 0, 0 minus negative constant. Because clockwise rotation about z-axis would be, we would have to rotate about the negative z-axis. So we'll have a negative constant at the third row, and all the other entries would be 0 because the robot is purely rotating. It doesn't have any component along lateral direction. Sorry, it does not have any component along longitudinal direction. It does not have any component along lateral direction. It will only have a component along the rotational direction. So again, what is the right combination? That's what the question asks. So it'll be, if we simply take out each of these options, minus root 3, 2 minus 1, 1 by L, 1 by L, 1 by L. So if we take the first option, omega, 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 and if we expand this matrix, what would we get? We'll get root 3 omega. This is negative root 3, right? Negative root 3 omega plus root 3 omega. So this will be 0. And the second row would be 2 omega minus omega minus omega. That will also be 0. And the third entry would be 1 by L omega plus omega by L plus omega by L. So this would indeed look like A by, sorry. So this would look like some A by 3 times 0, 0, 3 omega by L. But as per our question, we need a negative rotation about the z-axis. We would also expect a negative sign here. But with this combination, we won't be able to obtain the negative rotation or the negative sign. So we would have to flip all these angular velocities. We'll have to flip the direction of all these angular velocities. If you do that, we'll end up with this answer. We'll have a negative sign. So in that regard, the option 2 is the correct answer. Our second option, all the angular velocities are identical, but negative. I hope this is clear. I think we have cleared out enough problems in this pattern. So the basic expression would be zeta would be omega times omega. You would be given zeta. You would also be given omega. You would only need to find out the right combination of zeta. So multiple cases we have already found out. We have already practiced, and you are supposed to be finding out what the value of omega would be. So you can try out each of these options so that you will end up with the right requirement. Yeah, option 2 is the correct answer indeed. Yeah, and again, question 13 is basically a true or false question, kind of a thing. You are given two statements. An exact solution for controllable inputs for a given vector of system states can be obtained as, sorry, the first sentence we have forgotten to read. First sentence says for a robotic system with more stable system states than the controllable inputs W. So it says our kinematic relations is zeta is W times omega, and more system states means zeta would be greater than omega. So number of equations would be greater than the number of unknowns. So an exact solution for the controllable inputs for the given vector systems can be obtained. This is basically wrong, because the first thing would be we won't be getting an exact solution, because as I've already as I've already discussed, for an overdetermined systems, if the number of equations is more than number of unknowns, there are no solutions, and we can only get an approximate solutions based on one of the conditions that we tried earlier was the least square approximation. So yeah, exact solution cannot be found out, and also we cannot find out W by omega by W inverse zeta, because W inverse doesn't exist, because when M is greater than N, the W is not even a square matrix. So the first statement is indeed wrong. And the second statement says an approximate solution can be obtained by finding omega star such that it minimizes the least square error zeta minus W omega. So that is correct. We have already discussed that in the previous question. That is actually correct. And the third statement says the analytical solution to the above least square problem is omega star is W transpose inverse zeta. Again, for an overdetermined case, this is not the right answer. The correct answer would be W transpose W inverse W transpose zeta. This is the correct answer. We have already discussed it, where this is called left pseudo inverse. So again, option 3 is correct, wrong. And in this regard, then what would be the correct choice? Only statements 2 is correct. I hope the justification is clear. Yeah. And a similar question, but in the opposite sense, for a robotic system with more controllable inputs than the system states. So again, we have zeta equal to W times omega. And more controllable inputs means the length of omega would be greater than length of zeta, as in the case of a four mechanism wheel drive. So in this case, M would be less than N, or the number of equations are less than the number of unknowns. So in this regard, this is an underdetermined system. Underdetermined system. All right. So the first option says, first statement says, for a given system state with multiple system state, multiple controllable outputs can be possible. So given system state, zeta is the system state, omega would be the controllable inputs. It's not outputs, it's inputs only. So that is correct. For an underdetermined system, you will have infinite set of solutions. Not a singular solution, but not a single solution, but infinite set of solutions are possible for an underdetermined system. And the second statement says the control input with minimal norm is found by minimizing the objective function. Yeah, a norm of omega square plus lambda transpose zeta minus omega omega. So the way, if you want to find out the control input, we would basically select the solution with least norm, or we would out of all the infinite solutions, we would try and find out the solution that has minimal norm. Minimal norm or minimum length while satisfying this constraint equation. So we'll select the minimal norm solution such that it will satisfy the constraint equation. Yeah. And the solution for this objective problem to minimize this objective function would be you will end up with W would be W transpose whole inverse theta. This would be a solution, and this term is called right pseudo inverse. But whatever is given in the question is not correct. That is left pseudo inverse. That is not the case for an underdetermined system. So in this regard, the first I think first option is correct, second option is correct, and the third option is not correct. Because for the underdetermined system, we should be using the left pseudo inverse, but we should be using the right pseudo inverse, but we have the statement says we should use left pseudo inverse. And the correct answer would be solutions, statements first and second, not the third statement. Yeah, that is indeed the answer. Yeah, I guess we'll wind up with this. We have reached the end of this session, and if you don't have any further doubts, you may leave. But again, I would like to apologize for the lack of stability for this entire session. The internet connection is not stable as of now, if you had any troubles regarding my screen sync or my audio visual sync, please excuse for this time. I'll make sure that from the next instance onwards, it won't be a matter. All right. So yeah, if you don't have any further questions or any further doubts, you can. Thank you. Thank you. If you don't have any further doubts, you can leave.